Very informative.
Yeah.
Anybody? Thank you. I'm working on my reading, but I'm not there yet. All right, so I'm going to review a quick bit from Friday, okay? So the idea that you guys should have come across were a couple of things. IMFs, intramolecular forces, control what?
Boiling.
I'm going to just put physical properties in general, but specifically we generally look at what?
Boiling.
Boiling point is an example, and what? Anybody? Melting point. All those are like temperature related. Solubility, okay? So you probably saw that a little bit on your problem set. So IMFs, intramolecular forces, control the physical properties of molecules, meaning how hot we have to get them to boil and so forth. What are the three IMFs? Okay, London dispersion forces, dipole, dipole, and hydrogen. Dipole, and hydrogen bonding, right? So, in the case of when we would see hydrogen bonding occurring between two molecules, it has to be a polar or a nonpolar molecule?
Polar.
Polar molecule. What other one has to be incorporated into a polar molecule? Dipole, okay? So these are going to be with polar molecules, but sometimes we have to differentiate between the fact of hydrogen bonding and dipole. What are you looking for in that polar molecule to claim it's going to be hydrogen bonding? Evan. Ethan, sorry. Hydrogen has to be bonded to what? Fluorine, or hydrogen has to be bonded to oxygen, or hydrogen has to be bonded to nitrogen. So F, O, and N, I like to say hydrogen bonds are bonds, right? That's what I said in my video, to give you the chance to try to memorize that. If it doesn't have H bonded to F, H bonded to O, or H bonded to N, it's going to be then dipole. So what does that leave us here? Non-polar molecules only. Okay? So a nonpolar molecule can experience London dispersion. Okay, so now if I'm looking at the physical properties, the things that have the strongest attractions are going to have the highest boiling points, right? Strongest attractions, highest boiling point. Overall, of all the atoms or all the bond types in the world that we deal with, what's going to have the highest boiling point? Ionic, right? Okay, and then... All right, so ionic is first, and then now we're in covalent world. Which type of interaction creates the highest boiling point? Hydrogen bonding, because it's the strongest attraction between two molecules. Then dipole, and then London dispersion forces. Okay, so if you have two molecules and they both can interact through hydrogen bonding, how do you differentiate who's going to have the higher boiling point? What's the characteristic about them you look at? The mass, okay? So if you have two or more that are in hydrogen bonding situations, and you have to rank them like 1, 2, and 3 in terms of boiling point, you look at their mass. And the higher the mass, the heavier they are, the more energy is going to take to pull them apart. Dipole to dipole, same thing. You have to look at their mass. London dispersion, what do you have to look at? Anybody? Say again? Somebody said it. Look at number of electrons. Good. And so that's because dispersion works based on how electrons shift within a molecule. They disperse in a molecule, which can create some sort of pole. All right, so let's take this and apply this to the work you guys were, the chart you guys were working in on Friday. Okay, so pull up that chart from Friday, which had, somebody turn those in. Which had like the first one was NH3. This one. Pulls out. So don't look at it yet except for the drawings, okay? Don't look at it yet except for drawings. Did anybody else try one? I don't think so. Okay. No, I didn't watch it yet. Alright, so forgive me, I'm going to zoom past a couple things first. Oh, actually, hold on. I need to let you guys check this for a moment first before I move on, because I have not had a chance to erase from third period. Check your matching first. All right, almost there. So I guess since we're on problem set, let's keep looking at problem set, okay? So I'm gonna draw these as we go, just to give you some visualization of what we're doing. Can I move away from this for a second? Okay. So tell me the first molecule you guys were drawing, or structure you guys were drawing in the chart. SRF2, right? So everybody kind of walk through the process with me. SRF2. Look at SR on the electronegativity chart. There should be one kind of floating around someplace. SR's electronegativity. 1 fluorine. Okay, so if I had a bond between SR and F, it would have to be what? Ionic. Without a doubt it's ionic, because look how big that electronegativity is. It's a 3 difference. So how do you have to draw ionic compounds? Using the brackets and the charges. You cannot draw them connected to each other. So I saw many of these were wrong. Here's SR with 2 valence electrons. Here's fluorine. Here's another fluorine. Okay, so what do I do with them?
You combine.
I donate, right? I have to give away, transfer electrons to fluorine and fluorine. So overall, you could draw it as 2 separate ways. SR with a 2+ charge, fluorine with a -1. Start writing down this with me. Do not do this. Or it's distracting to the person next to you. You could draw those 2 separate ones as octet and octet, or you can put SRF2 to indicate there's 2 of them overall. So this does not have a molecular polarity. This does not have a molecular shape. This is not a molecule. It does not have any intermolecular forces either. But in ranking this is going to be relatively high or relatively low in blending? Super high, right? Because it's ionic. All right, what's the other ionic one? Let's draw these as we go. The other ionic one. NaCl, right? So NaCl, we have Na dot chlorine dot 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 dot. Okay, and then transfer electron, and what do we end up with? Na plus and bracket. Okay, so 7, 8 electrons, 1 minus. So if you want to compare the boiling point between ionic and ionic, what do you have to use as a characteristic? Mac.
You multiply the charges.
Good. So we call that charge product, right? So what's the charge product between these? 2. Okay. What's the charge product between these? 1. Okay. So what we would then rank in terms of the highest boiling point would be who? SRF2, because it has a higher charge product than this one. Okay. What's the next one on the chart? I don't have mine right in front of me.
NH4.
NH4. Oh, let's come back to that one. Go back to the next one. NaCl. Keep going. C. Say again. Oh, H2S. Okay. So H2S. How many valence electrons are we working with here? Come on, people. Talk to me. 8. Okay. So I'm just making sure we're all learning the process, or relearning, or reviewing, because I'm not just going to do the problem set on the board. You got to participate with me. Okay. So here's 8 valence electrons. What do I do now? Say again. S in the middle. 2 H's on each side. Okay. Who's happy already? Hydrogen is duet. We're good. Sulfur's not. What do I need? 2 lone pairs. Okay. How does it look shape-wise that I've drawn? It looks linear, right? Do we trust our 2D drawings?
No.
No, you have to defer to looking at the chart. What's the chart say for 2 ligands and 2 lone pairs? And so it really looks like this, right? But you don't always draw it right the first time, right? That's technically correct, and this is technically correct, but this gives you more information. So overall, you have, what's the electronegativity difference here? Was it 3? What is this? So is it 2.5? So we said we changed our chart so that 0.4 was in which category? Polar equivalent. So we actually have dipole moments pointing from what to what? Hydrogen to sulfur and hydrogen to sulfur. So up here we have a partial what? Partial negative, and down here we have a partial. So overall this is a what molecule? Polar molecule. Okay, so I'm reviewing this for like the 18th time. Pay attention. If we have a polar molecule, we have 2 categories of intermolecular forces we could assign to that. Hydrogen bonding or dipole-dipole. So what's the case here? Why dipole-dipole? Good. So hydrogen's not bonded to fluorine, oxygen, or nitrogen. Okay. All right. Next, give me another one else on the chart. Okay, this is the one I saw a lot of mistakes on. COCl2. How many total electrons? 4 plus 6 plus 14 is 24 valence electrons. Okay. Who's central? Carbon. And then how many attachments? 3. So I'm going to put chlorines left and right and put an oxygen here. Okay, what do I need to do for all of them? Octet. All right, so I'm thinking I got octet, right? Which one? So oxygen's got octet, right? What about carbon? No, right? So this is what I saw in some papers. So how can I modify this? Okay, so double bond versus this. Okay? So now I have 8, 16, 24. We're good. And everybody's got octet. What shape is this? What geometry? Trigonal what? Planar. Okay. So how did you guys assign the polarity to this one? Polar or non-polar? So you said that with a question. Some of you guys, who said non-polar? Anybody? Okay. I will stick with your gut. It's kind of weird because most of you guys I thought would say non-polar because we have dipole moments. I don't know what the difference is. Carbon is a what? 2.5? 3.0? 2.5. Oxygen is a 3.5. So that is a 1.0 polar covalent bond, definitely. And then what's the carbon to chlorine look like? 2.5 and 3, so that's a 0.5. Okay, so tell me why you guys said this was polar. Well, those are polar covalent bonds. Like this is pointing outwards towards chlorine, this is pointing out towards chlorine, this is pointing up towards oxygen. So the dipoles are pushing electrons up and out. So we got like a partial negative, right? Partial negative, that's for the one above, and then partial negative. So why did you guys say it was polar? Say again? Mac. Well, most of the time trigonal planar does allow for cancellation. It doesn't have to be 180 degrees from each other. It just has to be equally spread out everywhere. So if I had this with like boom, 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 and it was all partially negative all the way around, I thought most of you guys would say that was non-polar. I will go with this one as being polar because technically this one's a different size dipole than these two here. So technically it's polar, but that's probably more of an AP concept. I thought I was going to give you guys the easy route. Though looks like it's equally distributed, non-polar, but we'll go with that. There was some gray fuzziness in this one because we have some separate situations. There was another one like this, CH2O, right? CH2O. So, before I do that one, if you guys assign this as polar, what kind of IMF is here? Intermolecular force. Dipole, because we don't have hydrogen bonded to anything because there's no hydrogen. Okay, and then CH2O looks similar. How many electrons? 12 valence electrons. Carbon in the middle. Hydrogen on either side. Double bond O. Okay, shape of that one? Trigonal, planar, and the electron deficiencies or the electronegativity. Carbon oxygen is a what, 2.5 to 3.5, so we're pointing towards oxygen for sure. There's our dipole moment there. What about the hydrogens? Are those dipoles pointing towards hydrogen or towards carbon? Towards carbon because the electronegativity was like 2.1 and 2.5, so we're pointing inward. So overall, where's most of the negative charge? Around who? Carbon and oxygen. But if we're looking at like the extremities here, we got what up here? Partial negative, partial, and partial positive. Okay, so for sure, without a doubt, this one is what? Polar. And what kind of IMF?
Hydrogen bonding.
Where's hydrogen bonded to H? Or sorry, where's H bonded to bond?
C to O.
So no, H itself has to be bonded directly to F over N. Is that here? No. So even though there's a hydrogen, do not say it's hydrogen bonding. Hydrogen specifically has to be bonded to F over N. So this is dipole. Okay. Are there any others on there you'd like me to go over right now, drawings wise? And what? Na2O. So, oh yeah, that's what I wanted to do. Thank you. So Na2O. We have a metal and a nonmetal, immediately you guys should know what kind of compound this is. Ionic, right? Or if you didn't and you're just like, brain fart, let me check the electronegativity. What's the electronegativity of sodium? 3 point what?
0.9.
I was going to say, there ain't no 3. 0.9 and oxygen's at 3.5. So that is for sure in the ionic category. So I draw sodium. I'm going to draw it twice just to show the 2 present here. Dot, dot, and then oxygen here. How many valence electrons?
6.
Okay, so what do I draw with this one? Donation, and this one? Donation yet again. So in the end we make sodium, ion, and oxygen with octet. What's the charge on oxygen? -2. Okay. All right, so this is ionic. We don't assign a polarity. We don't assign a molecular geometry. We don't assign an intermolecular force. Yeah. Question?
Okay, so you wouldn't have Na in the mononucleates. It would just be there.
Oh, I'm sorry. 2 sodium ions. 2 sodium ions right there. Is that good? Okay. All right, so let's go back to the chart we were working with. Yeah.
Wait, so why isn't it +2?
Because each individual sodium lost 1 electron. So it changed its charge by 1. So then I'm going to put 2 of them here. Say I have 2 of them doing this. It helps to recognize the fact there's 2 electrons lost overall. Yeah.
I was kind of confused on how you determined whether it was positive or negative on the last problem.
On this one right here?
Yeah.
Okay, so the CH bond, look at the electronegativity. Do you guys have that sheet right in front of you? What is carbon's electronegativity?
Carbon is 2.5.
And hydrogen? 2.1, so the difference is 0.4, which is in the polar covalent realm. So I draw an arrow pointing towards the carbon, the dipole moment pointing towards the carbon to show the push of electrons towards carbon, push of electrons towards carbon, meaning there's a lack of electrons out here, and there's a lack of electrons out here. So that's why I'm calling this partial positive, because there's a lack of electrons. Okay? All right, so let's go back to the chart we were looking at just a minute ago, which was from our Friday notes, okay? So I just have to scroll through this for a second. Okay, so do not look at your paper, or don't look at your papers. Kind of cover up the left side of the, or the right side of the chart. Play this game with me. Cover up so we can like define our own molecular polarities and so forth. So cover them up with your arm or with paper. Cover up the right side of your chart. So I'm gonna borrow this for a second. So just look at the drawings. Just look at the drawings. Okay, don't cheat. Cheat yourself out of it. All right, so looking at your ammonia drawing, polar, nonpolar.
Polar.
Because there's this lone pair on the top of nitrogen that's not canceled out by anything else, okay? Water drawing, polar, nonpolar.
Polar.
Polar, because there's 2
lone.
it's bent and there's 2 lone pairs up there that are not canceled. CF4,
Non-polar.
because it's
Equally distributed.
distributed. What's the shape of that? Tetrahedral, if you had to go back and check that out, okay? This is ionic, right? So we're not going to put any polar or non-polar, it's just ionic. You can even put a slash to that. It may not be necessary to fill out. And PCl3?
Polar.
Polar, because there's a lone pair on top of the phosphorus, which is not canceled by anything else. Nitrogen? Non-polar and ionic. Okay, so here's your process. This is how your quest looks. You have, I think I even have 3 or 4, I can't remember, I put 3 or 4 compounds. You go through, draw their shapes, detect if they're polar or nonpolar, and then you're going to tell me about intermolecular forces and boiling point. So what IMF is present here? Look at your drawing.
Hydrogen.
Because hydrogen
Bonding
to nitrogen. So put HB for hydrogen bond. And then next one. Okay, H2O. And that one will undergo hydrogen bonding. And then just as a note to self, maybe you draw this with me as you go. Here's water, right? Here's another water. Talk to the person next to you and tell me where the hydrogen bond is.
Right.
Oh, CJ. Bag. All right, so call out the color that represents the hydrogen bond.
Green.
Green, okay, good. So we know that it's not a true bond. It's not the line attaching the H2O. It's the attraction between the molecules. I hate the word bond because it's a misnomer. So this is where the hydrogen bond is between the molecules. The H, which has the partial positive, is attracted to the O, which has a partial negative, like a kind of opposites attract, magnetic charge attraction. All right, so this is the hydrogen bonds. Ammonia, I could draw another ammonia molecule, and if we do the same thing. Next one, this one right here is nonpolar. What kind of IMF? London dispersion force. This one's ionic, so do we write an IMF? No. Okay, but we'll use that for later. PCl3, polar. Which way do I go? Okay, so dipole, because it's not going to be H bonded to anything because there's no H's in there even. Next, London dispersion and ionic, so nothing there, okay? So in ranking, who's the top rank? Ionics, right? So do you see we have two ionics? Okay, how do I differentiate between the two?
The charge.
Charge product for ionics. So you guys said the charge of magnesium would be what here?
1.
+2 charge, and chlorine would be a negative. Each individual chlorine is a -1. Collectively, you're right, there's 2 electrons change. But that's because magnesium lost 2 electrons, chlorine gained 1 each. So 2 times 1 is 2. Okay, and then this one down here, 1 plus and 1 minus. 1 times 1 is 1. Who has the stronger attraction? Mg2. So you get the number 1 boiling point. You are going to be quite high in terms of boiling point, like thousands of degrees. This one will get number 2 in terms of boiling point. It might be like 801, right? Some people did that in their comic. Is that right? 801? Yeah. Celsius. All right, so after ionic, who comes next in terms of boiling point? The 2 hydrogen bonding ones up here, right? How do I differentiate between those two? The masses. So everybody look at the periodic table. You might need one with masses on it, though, okay? What's the mass of N? Meaning nitrogen? Plus 3 hydrogens, which each weigh 1, so that's 17 grams. What's the molar mass of hydrogen? 1 plus hydrogen plus oxygen? 16, so that's total 18. Make sure the person next to you knows where to find masses on the periodic table. Make them pinky promise they know. Pinky promise they know how to find masses. I don't see any pinky promises. Pinky on these masses. All right, just making sure you know. All right, come back to me. Come back to me. Don't touch pinkies now. Please do them. Please do them. All right, so between these two, who has the higher boiling point? H2, because it has the higher mass, okay? And then the fourth one will be who? H3. Okie dokie. And then now, I've done ionic, I've done hydrogen bonding. Who's next? Dipole. I only have one of those, right?
Yeah.
So you've got to be number 5. Okay? And then now I've got to the final part. The lowest boiling points will be who? London dispersion. Okay, so how do I compare those? How many electrons did carbon tetrafluoride have? Count them up. 32 valence electrons, right? C plus 4 Fs. And then nitrogen?
14.
This is the valence. These are valence electrons, guys. Valence.
28.
You can count. I got you. Okay, 10 valence electrons. So, what you do on the London dispersion side of things is you look at the more valence electrons you have to shift around, the more likely you can create a partial positive, partial negative, which is why we call that dispersion forces. So the more electrons you have, the more likely you can do that, so you can achieve a higher boiling point with that. So this one's going to be number 6, and this one will be number 7. All right. Turn and talk to the person next to you for just clarification on some things. If you need it, then let's have a short question. Yeah, London's version of It's different every week. Can you guys come back in about 5? Thanks. All right, guys, come back to me. Let's do one more characteristic. We're doing great on time. So there was the idea that you guys were supposed to be able to predict what was soluble and what was not soluble in water. Yes? Okay. So the idea came from this phrase: like dissolves like, or polar things dissolves polar things. You might want to add this to your notes. We're going to do some examples, and we'll back up to that chart we just did to talk about solubility. So the rule of thumb is that like dissolves like. So this can be phrased as polar dissolves polar So I've just clarified that into 2 main categories. Polar dissolves polar or ionic, like just looks like or ionic, or nonpolar dissolves nonpolar things. Those are your 2 main categories, or 2 main phrases that like dissolves like is just describing. So let me draw this over here. So I've drawn 2 water molecules to help describe this process, and I've kind of just put circles around them. Alright, I'm going to draw a molecule in the middle of these 2 waters, and I want you to say yay or nay. Will water dissolve it, or will water interact with it? So here's nitrogen that we just had previously on our concept. What kind of molecule is nitrogen? Okay, so that's nonpolar. Okay, so can water interact with nonpolar things well? No. So will it dissolve nitrogen gas? No. And that's because water has this nice partial negative and partial negative right here, right? And then on the bottom it has what? Partial positives. So this doesn't have a partial negative or partial positive, so it doesn't have any way to interact with it because there's no like opposites track going on, right? So nonpolar things don't mix with water very well. That's why oil doesn't mix with water. Not only is the density not allowed to mix, but it also doesn't mix because oil is nonpolar, okay? So let's draw another one. Let's do sodium chloride. Will it interact with water?
Yes.
50-50, right? Go ahead.
Yes.
Yes, right? The sodium will interact with which side of water? The
Partially positive.
This is partially negative side, and chlorine will interact with the partially positive side because the opposites attract. So those will dissolve in water. That's why ionic things do dissolve in water. All ionic things will dissolve in water. And I say that they're polar because they are like the extreme of polar. What does polar mean? Unequal, like positive one and negative one. They are unequal in terms of their charges. Okay, and then what about ammonia? I'm going to squeeze this in here. Okay, what kind of molecule is ammonia? So you're looking at this. What's this shape? Look at the shape first. So 3 ligands, 1 link pairs, trigonal pyramid. So you got a pyramid, right? What's on top of the pyramid? So it's like super negative up here, and then not so super negative down here. So what kind of molecule do we have? Okay, so this is polar. So this side, which is partially negative, will interact with what? This partially positive side way down here. It's good, it would turn around actually. And then these hydrogens, which are partially what? Positive, will interact with what? The partially negative of oxygen. So if they can interact, be it like positives and negatives, they will dissolve. If they can't, they don't dissolve. Yeah.
Do you say that water dissolves?
Water dissolves in water is how we could say it, but it's just like, hey, water's water.
Well, like the other stuff though. Like, is water dissolving the other things, or are they dissolving each other? Why is water the dissolver instead of dissolving?
Because water has the ability to hydrogen bond, so it has a really very strong positive negative, so it actually does more of the work.
Okay.
But they just dissolve in each other. Okay, so I have a quick video for you. Got 2 quick videos actually. Garrett, will you hit the lights for me? All right, so.
The light.
No, you're right there. Go back to the chew one. All right, and movie watchers. Good? This is my favorite chemistry song ever. Ready? Hold on, you missed it. We saw you. Alright, I'll watch part of this now.
Something water in a bigger day. The ions broke apart in the usual way. Molecules want to get the ions apart. A salt solution formed, but that's only the start. Homogeneous, same throughout. Homogeneous, same throughout. Solvents that are polar can dissolve. Solutes that are polar or ionic, that is really cute. Water and nonpolar things just won't mix, but a nonpolar solvent like an E can fix. Like dissolves light, polar and polar. Like dissolves light, nonpolar and nonpolar, and all the solvents.
You guys saw that, right? Yeah. Oh, wait, you didn't see it? Wait, you didn't see it? My favorite part. Hold on.
Homogeneous, same throughout. Homogeneous, same throughout. Solids that are polar can dissolve. Solutes that are polar or ionic, that is really cute. Water and nonpolar things just won't mix, but a nonpolar solvent like an E can fix. Like dissolves light, polar and polar. Like dissolves light, nonpolar and nonpolar, and all the solvent molecules used up and are stuck with the solute ion in your cup. Solution saturation.
Okay, we'll do the saturation point later. And I got one more. No, this doesn't apply to what we're learning, so I don't want to confuse you. And then I gotta find my other video. There it is right there. This one's exciting.
When an ionic substance, such as sodium chloride, is placed in water, water molecules interact with the ions on the surface.
Oh, really?
If the salt is soluble, the attractive interactions with water molecules overcome the ionic attractions within the lattice. The solvated ions move off the surface and become separated in solution. Notice that water molecules cluster about the anions with the hydrogens directed toward the negatively charged ion. On the other hand, water molecules interact with the positively charged cations through the lone pairs of electrons on the oxygens.
Okay. What's this one? Oh, that's like a minute. You guys have that.
It's mostly just introduction.
Is this one? Une molecule d'eau.
It's just a little quiet.
This is just thrilling, guys. This is thrilling.
Is it still going?
I am captivated.
Mini.
guys learning? Are you guys learning the?
And Donald Duck.
All right. Well, that was exciting. Well,
The introduction was one.
okay. So, all right. I'm gonna kind of do some shifts while some people are writing this down, just for the clarity of understanding why water and oil don't mix. We're gonna grab a laptop. Three people grab a laptop again. Laptop. Before I grab a laptop. Try to go in shifts here. Okay. And then, let me see.
Sodium chloride crystals are
Still
Oh,
playing.
that one's hot.
Okay. All right, next folks, go grab your laptops. Well, Evans. Last people go grab your laptop. Alright guys, just log on for me while we finish up our notes. Alright, so the last bit for just regarding polarity and the properties of those compounds was solubility. So you should be comfortable identifying the highest to lowest boiling point, and then are things soluble in water, yea or nay. So ideas that non-polar things can mix with non-polar things really well, like grease and oil and methane, they often all blend together, but they will not mix with water, okay? So let's go back to the chart we were just working from, which was from Friday. The chart we were just working from Friday, and let's write down who is soluble and who is not soluble. So everybody tell me, ammonia, soluble or not soluble in water? Because it's polar and water is polar, okay? Water, soluble in itself, yep. CF4, not soluble, so I'm going to put NS. So it's not soluble in water because it is what?
It's
Non-polar. Ionic compound? Soluble because polar, or ionic dissolves in polar. And then next one?
soluble.
Soluble because it's polar. Nitrogen?
Not soluble.
Not soluble because it's not polar. And then soluble because it's ionic. So you should be able to identify who's soluble and who's not soluble based on if it's polar or if it's ionic. So yeah, that's what you'll be expected to be able to do tomorrow. All right, is everybody logged on a computer? Go to Kahoot.
I'm never good at these.
All right, go to Kahoot. Doesn't matter, doesn't matter. Oh, the Lord.
Mine won't even turn on. Okay, now it's turning. Oh.
Alright, so here are my rules, and I don't think, we played Kahoot like one time together, but here we go. I had to cut it off in the last class because they were misbehaving. So between questions, have your little like minor victory, like this. Keep it calm. And I'm going to talk about the questions. I need to make sure people got it wrong and understand. Or if you accidentally got it right, it doesn't mean you know it. It means you got lucky. It doesn't mean you're always going to be lucky. So pay attention between sessions or between questions. And I have the ultimate power to get, like, if there's 5 seconds left, I will skip you if you don't answer it. Because some of these questions, there's too much time allotted, so you may not get that question. Just put initials here. Always. As long as I... Are you a good...
I'm an amino acid.
I do. As long as it's not vulgar and I can figure your name out. Alright, and the rest of you, 5, 2,
Hold on, I'm trying to
1, 7, 7, 6. That's the game. 5, 2, 1, 7, 7, 6.
the last second.
I'm gonna erase this one. Who's this?
It's Parker. It's Parker.
Oh, you guys are ridiculous. Who's not about? Who's this?
Robbie Robin.
Who's this?
Locash. Who's Locash? How do we have 36 in this class?
I don't know.
Who are these people?
Okay, what I'm really no, I don't know. Alright, we're gonna go ahead and start. That's so weird. Alright, get ready. Which bond happens between S metal and N non-metal? Metal and non-metal. Metal and Okay, and your minor victory, you get your little woohoo, and then we're done. Ionic is a metal and non-metal. If they are on the most of the left-hand side of the periodic table, from like aluminum to the left, it's a metal. And if you're combined with a non-metal, you're ionic. Metals in bonds are always wet. Metals, when they are bonded, are always wet.
Alright, I'm gonna
Alright, you got 5.
They're always shiny.
Alright, minor victory. So this is basically saying, eyes, no dapping up, you good? Okay. Alright, so cations are forming because metals all have less than how many valence electrons? How many valence electrons? Well, yeah, we can say less than 100, guys, but let's get specific here. Look at the metals. They're over here. They all have less than 4. So if you've got less than 4, are you going to gain?
No.
No, you're going to lose electrons, which makes you a cation.
Yeah.
Okay?
I knew that for sure.
All right, moving on. Which type of bond shares electrons? This should be fast. Oh, wait.
Can you explain this?
Noise.
Yeah.
Back to me. Back to me. Guys, thank you. So non-metals will share electrons as making a covalent bond because they have to get octets together. So next, which type of bond is the strongest, causing high melting points?
How long is this?
Alright, let's get the rest of you. Alright, Ionic, good job, good job. Which type of bond is between 2 or more nonmetals? Between questions, you gotta pay attention.
I'm gonna go with all of these. It's mostly questions.
Okay, guys, I literally just said that before this question. I said 2 nonmetals make covalent bonds. Pay attention. Why do elements bond?
Be together.
Multiple choice question.
No, I actually
Gosh, doggy.
So if this was a multiple choice question, you all would have got it wrong because the best answer is all of the above. But true, you are correct. It's just not the most correct. How can electrons participate in the bonding process between elements?
I'm putting all of them this time. Right last time. This time. Yeah.
Okay, I didn't click it actually. Okay, so if they are transferred, what kind of bond is it? If it's gained, if it's shared, covalent. Next.
I almost clicked the A1. And then I remember
Okay, back to me. I got 9 people. If you're one of the 9, you got to think losing electrons makes you less negative. If you're less negative, you're technically positive, like a cat ion. Okay. Oh, it's you. I want to know what you know. Let's go. Stagnant, sorry. Moving along. Which of these ionic formulas is written correctly with the cat ion first? Look closely. Right. Thank you. So we actually did that question earlier in class, so we've done magnesium chloride a lot, but what should you be looking for to identify as an ionic compound, Langston? A metal. That's the one with a metal, right? This is 2 nanometals, right? What's that?
This is just one.
That's just a non-metal, a noble gas, and this is
Just
which still is just a metal, right? It's just a metal. It's not a combination between a metal and non-metal. That's the only one that does that. This is what you would have on multiple choice. So quest tomorrow, no promises, but I think it's 7 multiple choice questions, which would be like identifying characteristics or identifying which is which is conductive in solution. Well, it's going to be ionic. You look for the one that's ionic, and the charge. Okay, moving on. Which of these is a covalent compound? All right, let's keep going. All right. Okay, guys, look up here. Is that point? Look up here. Is that point? What kind of compound is this one? Why is it ionic? Metal, non-metal. What kind of compound is that one? Metal and non-metal. So it's ionic. This one? Metal, non-metal, ionic. This one? Non-metal, non-metal, covalent. Moving on. Which type of bond? Which type of bond usually results in gas and liquid exchange? Alright, okay.
I keep saying a fish.
Come back to me. So all the metals, I don't know if you chose metallic, all metals are solid except for one, which is mercury. No metals are gases. That would be poisonous to our lungs. Okay, so definitely not metallic. Certainly covalent.
Oh, this is gas?
Yeah. I hope you're reading.
I think I read that.
All right, guys. 3, 2, 1. Okay. So think about this. If you have, guys, some water and you put salt in it, sodium chloride, it will ionize into sodium ion and chlorine ion, and electricity can flow through that quite easily. But if I drop a quarter in some water, is the quarter going to dissolve?
No.
No, okay? So the quarter itself is a solid. It's not going to dissolve, so it will not make the solution conductive. It's certainly conductive in a solid state as well. So that's the difference between ionic and metallic. Ionic is only conductive in molten, meaning liquid state, or aqueous, meaning mixed in water state. But metallic is conductive when?
Oh, I want to solve it.
As a solid, right? Or as a liquid. But not really as aqueous because you can't dissolve metals in water. You cannot. Next.
Miss Samuel,
Answer. Yes.
can I have a lithium line for dismissal?
Thank you.
Thank you.
It's the last thing we just talked about, people. Most of it was ionic was going to be soluble or polar covalent, but we didn't differentiate between covalent, so you couldn't just put a blanket statement on covalent, okay? So definitely ionics is soluble in water in general. Next. Stand up. Yes, okay. Pass to me. 3, 2, 1. Malleable and ductile, those characteristics definitely go with what kind of bonding? Metallic, like nothing else. Shatter, like a brittle and shattering would go with what? Ionic, which a lot of you guys chose. That's a non-ionic because it's metal and non-metal. That's just metal because it's just a metal. I got, I think, one more. 2, yeah, okay. Hold on. I know. All right, last run, Raven. I don't know who that is. Okay, come back to me. So again, what are we looking for? Just a metal. That is not just a metal. That is what? What kind of bond is this? Metal and non-metal. So that's ionic. That one? Non-metal, non-metal. So that's what? So my people who are not participating, I hope that you get this right tomorrow. Okay? So this is C and F, which are 2 non-metals, and that's just a metal. So it's just metallic. All right, and here we go. We're going to put laptops up in the hot second. And get the results here.
It was Serena.
Well, I got third.
Don't hate. Don't hate.
I got third.
Don't be jealous. Just work harder. Just work harder. How do I go back to the leaderboard?
I got third.
That's a personal question. All right, guys, and all right. Side notes. You guys can do those later. So, first couple people over here log off. So this side of the room log off. Put your laptops up. Everybody start writing down the rest of our notes. We have about 15 minutes left in class. 20 minutes left in class. And then we're gonna wrap this up early. Wrap this up early. I think I've got about 4 slides left, okay? 4 slides left, and bring some examples and better. So log off for me. Start thinking. Thank you guys for putting them in the right place. You see those scores are right. you guys can ask about that? Serena's row. Actually, everybody knows. Yeah, go ahead. Guys. Alright, so you guys are finishing writing this down. We're going to talk about these quickly and then we'll be done today. Well, I've got some examples to go through next. I'll show you pictures. I wouldn't say that's exactly. We don't have a line like that. It can still be like disoriented. Okay, so who's already finished this? No. All right, I know some different places. So we haven't really talked about metallic bonding in depth, but we do know they have very, very unique characteristics. Always with me? Okay. So metallic bonds have very, very unique characteristics, and what we have to be able to do is talk about how the structure of metallic bonds controls those unique properties. That's really the heart of this. How does the structure of a metallic bond impact its properties? Ionic, we kind of know there's the same thing. Covalent really does the same thing, but metallic has they have such unique characteristics. So what happens is we have an interparticle attraction. So silver was the last example on Kahoot, right? So I'm going to draw an ionic kind of bonding situation. We have all these silver ions. They're positively charged because they've done what with their electrons? To a big pool in the middle, right? And they're delocalized electrons kind of floating around. So I'm going to kind of draw this as a big pool. And there's electrons just floating around everywhere. They're just everywhere. Are they localized in one place? No, what's the word for that instead?
Delocalized.
Delocalized. Electrons, they say that they can float around everywhere. So I'm going to kind of put like little quotes, I don't know, around them. This basically just means that they can move from these locations, so they're mobile. So the electrons can float around, and that gives them very, very unique characteristics. We say this forms a sea of delocalized electrons, or a sea of mobile electrons is another way to say that. And the mobility of electrons allows for unique characteristics. What are some of those unique characteristics we've already spoken of? Matt. In what? What state? Solid state, which other things are not conductive in solid state, they just are not. What's another unique characteristic, Josh? Malleable. What's another unique characteristic, Alex? We said conductive in solid state, malleable. Shiny. Their electrons arrangement doesn't give them a shiny appearance, but they have another unique one. Anybody else? Yeah. Ductile, right. So that's the basics of how does it work is all because of the delocalized electrons. All right, give me a thumbs up and I can move on from here. Just about. Okay. And notice that the electrons, I'm showing them kind of floating around everywhere. They could potentially move to one side or the other, but they kind of stay dispersed throughout. All right, so I can come back here if I need to. Questions?
Yeah, so will their boiling point be higher than ionic or lower?
They're really close. They're on par with ionic. It kind of depends on how many electrons they lose and how good the charge product is in ionic to kind of differentiate from there. So we just say high because it's up on the same level of ionic. All right, so that's kind of what the electrons kind of look like. So one person said conductive. I think that was Matt, right? So conductive to not only electricity, but what else are they conductive to? I don't know what I'm writing here. Electricity and heat. And that's because heat is a wave, like it's energy, and electricity is energy. So what can happen is, like an electron, which is what, you guys know electricity is just electrons. You guys know that? Okay, well, the electricity that's coming through the wires up here are just electrons. The entire internet, think of how big the internet is. Like, the internet is just a bunch of electrons hitting a little detector. That's it. And it weighs, like this was quoted maybe like a decade ago, so it could be bigger than this, like certainly by now. But all the electrons in the world that make up the internet weighed about the mass of a strawberry. That is a lot of electrons, but a strawberry makes up my entertainment for my life. Like, a strawberry's massive. Like, that's insane. Maybe it's like 2 strawberries now, and like I might not be giving all the credits due, but 2 strawberries make up the entertainment of my world. That's crazy. Yeah. So the electrons, regardless, can move and bounce to all these electrons and these charges, which give it the ability to allow for conductivity or electrons to flow through or heat to flow through. Question. Stuff about metallic bonds, the characteristics, yes, because it's just the characteristics. I'm just elaborating on them. Okay. Okay, so the conductivity, thermal, and electric, and malleable and ductile, those are all explained by how the delocalized electrons kind of can relate to each other. Okay. So one thing, and I've already explained this one because I just drew that picture with the electrons bouncing around, they just can flow through the charge quite easily. Malleable means what? Shout it out. A little bit more than that. Flatten out. Okay. Okay, so to flatten out into a thin sheet is what malleable means. What's ductile mean? Pull it out into a wire. Okay. So what happens, and we were demonstrating that, okay, so this means flatten out or stretch into a wire. Ionic compounds, if you bang on them, what are they going to do? They're going to shatter because they're brittle. They don't last very long. Metals or metallic bonding, what happens is as you flatten it out, the metal and the electrons just kind of line up next to each other. And they kind of just hang out, and they can move, and they can kind of squish next to each other. But as you flatten it out, they just kind of get closer and closer and closer together, but they can move. And that's because of the delocalized electrons, also known as mobile electrons. If we didn't have mobile electrons, the metals themselves would look just like ionic, and they would smash and then crash, and they would be brittle in the same sense. So that when you flatten things out or when you pull them to a wire, the atoms of the metals and the electrons are just kind of lining up next to each other and filling the gaps in between. So this is in contrast to ionic, and this is like the main point. This is contrasting ionic because we use the word static to say that in ionic bonds, electrons are in one place. Can they move? Yea or nay? Can electrons move in an ionic situation? No, they are on the anion, and that's it. They cannot move. But in metallic situations, they are mobile, so they can move. And that's why they have starkly different characteristics. Give me a thumbs up if this makes sense, and I can move on. All right, so some of you guys are still right. Who's ever heard of an alloy? Give me an example. Anybody? Steel, sterling silver, steel, bronze. What else? Gold, 14 karat gold. Nobody's gonna start singing. Okay. All right, we're done. Keep your day job. So 14 karat is not truly all gold. It's a mixture of silver, tin, nickel. It's just a blend of metals. So that's our last bit here. Okay. So alloys, and this was actually on the first slide as well. Alloys are a blend or a mixture of 2 or more elements, one of at least which is a metal. These examples you should be able to tell me a little bit more about them. So I'll let you write down that first and we'll talk. Okay? So I'll give you 2 examples. Cast iron and bronze, which are the Statue of Liberty there. As you're writing, think about why would they want to do this in metal? Like, what's the purpose of this blending thing? Talk to the person next to you as you go.
It's a lot more durable.
Unbreakable.
Alright, come back to me. Come back to me. Alright, so raise your hand if you're wearing something metal or you have some metal object in your possession. Okay? Who can tell me what it's made of? Parker.
A coin as a penny is made of copper.
But it's an alloy, right? Copper and what? What's on, does anybody know what's on the inside of the thingy?
Metal.
Wow. Specific.
Aluminum foil.
Metal. Zinc. Good job, guys. Zinc on the middle. Okay. What do you have? Aluminum? Is there any other alloy? It just says aluminum? It might just be aluminum, but aluminum is pretty flimsy, right? You can dent aluminum quite easily. That might not be the most desirable unless you're just like keeping your watch out and you like not really banging out anything as you need. What else?
This metal.
Bone, polyaluminum, and there's all kinds of stuff on the inside I couldn't tell you. But what else? Sterling silver, made up of silver, should be right. Maybe a teeniest bit of nickel or gold or cobalt.
And sterling.
Okay. On sterling. Okay. Can you guys quickly tell me the atomic number of bronze on the periodic table?
Bronze is not
Dang it. Caught me. Okay. So bronze is not on the periodic table because it's not an element. Shh. Back to me. It's a blend of two elements, copper and tin. So I heard some characteristics or things that you guys were denoting. Shout them out for me. Why would we want an alloy?
Stronger.
Okay, stronger, so you mean durable? Bless you.
What rust?
Okay, guys, you with me? You with me? All right, so we got durable. What's another one?
That's not rust.
So eliminate rusting. What else? What, so durable, eliminate rusting. That's all you guys got?
I got one of them.
So maybe something that would conduct or hold heat better. Okay, making things pretty, shiny, right? Is what you said? What else?
Making it cost something cheaper.
Okay, so eliminating cost or decreasing cost. These are some reasons you guys should know about why we make alloys. It's not just because we're like, oh yeah, we're alchemists, let's make some alloys. There's a reason for it. So here's a couple of examples. So we have cast iron. So cast iron is actually a combination of iron and carbon. Iron itself will rust. So when we add carbon to it, it eliminates the chances of rusting, and it makes its specific heat is actually like how long it can hold heat. It holds heat really, really well. So what did they cook on back in the day? Cast iron, because did they have a stove that was going to stay just heating the whole day really well, like an electric stove? No, they had a wood fire, and eventually the wood would, be gone or burned out. So the cast iron skillet would hold on to the heat and keep things warm from breakfast to dinner without using any electricity. And so that was valuable. Bronze, which the Statue of Liberty is technically made of bronze. What's on the outside of her?
Paint.
What's this? What's the green stuff?
Copper. Bronze.
Tin.
It wasn't green.
Patina. Okay.
Oh,
Didn't have anybody do it.
Paint.
All right, come back to me. So patina is actually a rust form of copper. Rust is the technical term for iron 3 oxide, which is iron and oxygen. So what happened was oxygen's been bombarding the Statue of Liberty along with other things that deteriorate the outside, acids and other things like that. And so the copper has made a copper oxide, which is green. It's called patina, and it's on the outside of her. But on the inside, she's bronze. She's that goldish, brownish kind of brown color. So copper and tin make this really desirable characteristic. It actually eliminates, diminishes the reactivity of copper. So if you eliminate some of the reactivity, the statue will exist forever, like a very long time. If you have something just made of copper, it will react with the air in the atmosphere, and it will decay in no time at all. So who's ever seen, like, maybe on jewelry, let's go back to jewelry, like something that's nickel-free, like a nickel-free earring, or, yeah, because some people are allergic to it. Do you know what it does to them?
Makes them green.
It turns them green. It turns their fingers green, their ears green, their necks green. So they're allergic to it because the nickel in it is very reactive, just Ni nickel. So if it's nickel-free, it eliminates the chances of reacting with your skin, because your skin has oxygen and water and other chemicals on it that would react with it. So the reasons we make alloys are durable, eliminate rusting, conduct or somehow storing energy better, eliminate cost, and reactivity, diminish reactivity. So girls, guys, when you're getting some sort of ring or other kind of piece of jewelry, tell these people, whoever's getting this for you, that you don't want a 14-karat gold one. You want like a 6-karat gold, like a 5-karat gold. Because gold, what's one cool property about gold that you maybe see like an Olympic medalist get or see? They bite it, right? Have you guys ever seen them bite the gold medal? What happens? You can see the bite marks in it. Do you want like a watch or a necklace that's like bending on you? No, like falling, like breaking and falling off. So You don't want something with a lot of gold. You want something with a little bit of gold because the rest of the stuff that's in it will make it more durable and stronger. So just tell them you want the cheapest thing on the rack. You don't need that 14 karat gold. You don't. Okay? Or the 24 karat gold. You don't need any of that. Okay? All right, go ahead. We can pack a little early today. Pack a little bit early.
Call for the buses today. Bus 320 would be bus 387. Bus 387, students, your bus will be 10 to 15 minutes late. Students are the waiting time, or you may call home. Thank you and have a good afternoon.
Is that a note for that filter?
I haven't got you for sure yet. When is that due?
No, it's after turning it today. Like, on the way to the bus.
Alright, my last announcement, okay? 3, 2, 1. Leave my little electronic activity sheets. I need these for request tomorrow. Tomorrow, you guys have third period hush. Tomorrow, you guys have third period intervention. Because they want us to do Wednesday second period intervention so that our PSAT goes from first to second, and then we stay in intervention until everybody finishes the PSAT. They don't want people moving around. Okay? So Wednesday, you will not see me for intervention. Tomorrow, you will see me for intervention. Yes? My bad. Never mind. Fun fact, your third and second is switched tomorrow. You good? Okay, hold on. I'm still not done. I was thinking it was my third and second.
Okay, third and second intervention is switched.
So tomorrow, hold on. I'm waiting for people to be quiet. I'm gonna wait. Okay, so tomorrow, Tuesday, you have third period intervention, not second period intervention. Wednesday, you have second period of intervention. Thursday, you have fourth, and Friday, come room. Wednesday, since free intervention PSAT. Okay, I know you'll be sitting and kind of grinding away at stuff for a while. I'm going to try to do a really fun lab on Wednesday, but I got to see if I can prep it because I'm administering the PSAT, and I may not be in here to prep the lab, but it's a very prep-heavy lab, like it's got zinc powder, which is flammable, thank you, and a couple of other things. So I'd like to be able to make a prize, like your prize possession for chemistry on Wednesday. That means I need you to bring in a penny. Okay, can you bring out a penny? Yeah. Okay, put a note to self on calendar. Bring penny Wednesday.
Would somebody just bring extra penny just in case?
Somebody to put the penny on anybody else. You guys can bring penny.
Oh, not for me.
Okay, now the rest of it is yours to do what you need to, but your quest is tomorrow. Your quest is tomorrow. Do not stand at the door. Do not stand at the door.
I just realized I have a tutoring session at the library today, but when's the next time this week you have it?
Let me look back out.
Okay. I have to use the bathroom.
I'm gonna
let you do great.
Guys, okay, listen. Step back, away from the door. Do not let the door ever there move. Everywhere moves. Put my toy down. Thank you. I have a couple more people asking me good questions. One, if your name's on the board, Langston, Hunter, Emily, I need stuff from Friday. I need the assignment from Friday, turn in the box, you do turn in Friday. Second, your quest tomorrow is a combination of, Hunter, you with me? Yes. Alex, you with me? What did I just say? Didn't think so. Do not laugh at me, pay attention. So your quest tomorrow is a table. The table has 3 to 4 compounds. Drawing the structure. Tell me the shape, like geometry. Tell me if it's polar or non-polar. Tell me its IMF, of course. And then order it with. And then tell me which is soluble in water, meaning polar water, yea or nay. There are 6 to 8 multiple choice questions, mainly based on characteristics that you had in that big, huge bonding chart you guys did the very first day of this year. So know your characteristics for ionic, covalent, and metallic. I did not give you close reading because you guys did well today until the very end. Hold on. Study for your quest. Text me questions. Come see me tomorrow from YouTube class.
So we do. Hey, my name's Spurs.
Yeah. All right. I'll see you. I'll tell you later. Okay.
Okay. That's amazing.
It's just so
Well, you're missing too much work from me. I'm almost certain. I have to pull this up. What else?